In this video, we will begin our deeper look at elimination reactions for the preparation of alkenes by focusing on dehydration. Let's look at a few examples of dehydration reactions. Here we have ethanol, and if this is treated with concentrated sulfuric acid and heated up to 180 degrees, the product that is obtained is ethylene. Note this is a primary alcohol, and we also have water as a byproduct. We usually don't care about that. We focus on the organic species. In our next example, we have cyclohexanol. This is a secondary alcohol, and if this is treated with 85% phosphoric acid heated up to 170 degrees, the product obtained is cyclohexene. And in a third example, if we have T-butyl alcohol, which is an example of a tertiary alcohol, this can be treated with dilute sulfuric acid, warmed up a little bit, and this will give as the major product this alkene, 2-methylpropene. So we can see that dehydration works for primary or secondary or tertiary alcohols. It doesn't work with methanol because you can't make an alkene when you only have one carbon. But dehydration can be carried out on primary, secondary, or tertiary alcohols. The relative reactivity that has been observed is that tertiary alcohols react faster than secondary alcohols, which react faster than primary alcohols. We can see this in the conditions that are being used. So for a tertiary alcohol, which is the most reactive, we have acid and it's heated up a little bit. For a secondary alcohol that is less reactive, we have stronger acid and it has to be heated to a higher temperature. For a primary alcohol that is the least reactive, we need the most concentrated acid and we really have to crank up the heat to get the reaction to proceed. Now, there are other methods that can be used, other reagents that can be used to convert alcohols to alkenes, but we are going to stick with this traditional approach. And so in general, whenever you see an alcohol being treated with a strong acid, such as sulfuric acid, phosphoric acid, potassium hydrogen phosphate, etc., plus heat, I want you to think dehydration for the preparation of an alkene. Now here we have another example of a dehydration reaction. So once again, we have an alcohol. This is a secondary alcohol, and it's being treated with sulfuric acid and heat. Because we're doing this on paper, I usually don't get into the specifics of how concentrated the acid is or how high the temperature is. I'm just giving the general conditions. So one thing that's important to consider is that for this particular secondary alcohol, this is our alpha position, this is the beta position, this is also a beta position. And another thing that you should notice is that this beta position is not the exact same as this beta position. So when we have multiple beta positions that are not equivalent to each other, we have the possibility of forming different products. So for example, if we lose one of the H's from the red beta position along with the OH, then we are going to make this alkene. But if we lose one of the H's from the blue beta position along with the OH, we are going to form this alkene. And so two different products are possible. For this particular reaction, these are formed in the amount of 97% compared to 3%. So this is an example of a regioselective reaction, when a reaction can occur in different locations, but shows a preference for one location. So this reaction could occur here or here, but there's a strong preference to occur here. So whenever we have an alcohol with non-equivalent beta positions, then we need to apply Zaitsev's rule. Zaitsev's rule tells us that based on empirical evidence, when multiple products can be formed in this reaction, the preference is for the more substituted alkene product. So these reactions are regioselective, preferring the more substituted alkene. Looking at the red product, this alkene carbon is connected to 2 hydrogens. This alkene carbon is connected to 1 hydrogen and 1 carbon, so this is monosubstituted. The blue product, this alkene carbon is connected to an H and an alkyl group. This alkene carbon is connected to an H and an alkyl group, so this is disubstituted. The disubstituted product is preferred over the monosubstituted. Now, another thing you should notice regarding the blue product, this alkene carbon is connected to 2 different groups, the hydrogen and the methyl. This alkene carbon is connected to 2 different groups, a hydrogen and a methyl. Whenever our alkene carbons are both connected to 2 different groups, then they can exist as cis and trans isomers. So what I wrote here in blue is not specific enough. This can actually be formed as the trans product and as the cis product. So now let's update our percentages, and these products are obtained in the amount of 3% of the monosubstituted, 74% of the trans disubstituted, and 23% of the cis disubstituted. So in other words, this reaction is also stereoselective. So when a reaction can produce multiple stereoisomers, but shows a preference for one particular stereoisomer, then it is a stereoselective reaction. And so trans is preferred over cis. Now, on the previous slide, I said that when we see an alcohol plus a strong acid plus heat, we should consider the possibility of dehydration. But now we need to add a little information to that. So when we see an alcohol plus acid plus heat, we need to think dehydration. We also need to look for the presence of non-equivalent beta hydrogens, because these can lead to multiple products. If we have non-equivalent beta hydrogens, then we need to apply Zaitsev's rule. In addition, we need to look for the possibility of stereoisomers. And if stereoisomers can be formed, we need to recognize that trans is preferred over cis. Before we move on, let's take a look at one more example. And once again, we have a secondary alcohol treated with phosphoric acid and heat. Notice we have 2 non-equivalent beta positions. So remember, this is our alpha position, the carbon where the functional group, the alcohol, is connected. And so this is a beta position, and this is a beta position. Now, the blue beta position doesn't have any hydrogens, so we can't lose H and OH to form an alkene here. So instead, we have to lose an H from the red beta position and the OH here to give an alkene at this position. So we would expect to form this as our major product. What's been found experimentally, however, is that while this product is obtained, it's only in the amount of 3%, while the other products include this alkene in the amount of 64% and this alkene in the amount of 33%. So yes, we get the expected product, but we also get other alkenes. Well, these are alkenes, so why didn't we expect these? What you need to notice is that what we're looking at here is a different carbon skeleton compared to what we started with. Right here we have one carbon that is connected to 4 other carbons, but in these 2 molecules, we don't have any single carbon connected to 4 carbons. Furthermore, this carbon was connected to a methyl group, but now this carbon is connected to a methyl group and another methyl group. So we had a rearrangement. This provides evidence that this reaction probably proceeds through a carbocation. And so we can account for the formation of these products through a carbocation rearrangement. So on earlier slides, we said that when you see an alcohol plus a strong acid plus heat, we need to consider that this is a dehydration reaction. Furthermore, we know that we need to be on the lookout for non-equivalent beta hydrogens, and then we apply Zaitsev's rule, knowing that the more substituted alkene is the major product. We need to be on the lookout for the possibility of forming stereoisomers, and we need to apply the fact that trans is preferred over cis. Finally, we also need to consider that there is a possibility of carbocation rearrangement. So by looking at these examples, we've seen the conditions, we've seen some of the features of the reaction. In our next video, we're going to take a look at the proposed mechanism for the reaction. Now, it has to be a mechanism that can explain why these things happen.